Okay, so it is a great pleasure to introduce our second speaker of this afternoon session, Dr. Jing from Northwestern University, and he's going to talk to us about a particle scale force approach to granular segregation. Thank you very much, Lou, for accepting this invitation. It's a pleasure to have you here. Please start your talk.
Okay. Yeah, so first of all, I want to say a few words for Yuri. Thank you for the invitation, and thank you for the organizing this seminar and bring together so many researchers that I respect very much in the field. And today I'm very happy to talk about our research at Northwestern about a particle scale force approach for granular segregation. And this work is done by me and my colleague Yifei partly under the supervision of the professors listed here. And so first, particle segregation can be found very commonly in industrial processes and geophysical flows. And interestingly, the two examples I show here, the first one is from our lab at Northwestern, who focused a little bit more on industrial applications, while the other one was the work that we did together at the University of Hong Kong during my PhD, where people concerned much more about geophysical flow, like debris flow, where segregation also occurs. And besides what Chris presented this morning in much more details. And then if we look at the modeling of granular flow, especially in a continuum sense, we can look at this idealized slope where particles of large blue particle and small red particles flowing down together along the slope. And then one of the microscopic mechanism of how segregation occurs during the flow is the kinetic sieving, whereby small particles percolate through voids while displaying large particles to the surface. And then in order to model this at the continuum level, we will have to, one of the very common approaches to use this transport equation where we describe the evolution of the concentration C with different mechanisms such as advection, segregation, flux, and diffusion. So here the advection and diffusion are pretty standard for any transport problem, but the most important thing here special about segregation is the segregation flux model, where we will need some sort of constitutive relation to describe how the segregation velocity depends on different conditions. And then this is one of the examples that using this approach in our lab to simulate the segregation, evolution of segregation on the flowing layer. That's what we observe in this box along the surface. And then there are a lot of actually recent review papers on this topic, different groups. And even though it has a lot of success in modeling segregation in different configurations, but there are still a lot of challenges remain for this problem. So one of the challenges is that from what we observe in lab, actually evidence has been there for a long time that although usually we consider large particles to rise to the surface, but actually large particles do not always rise. It depends somehow on the density ratio and size ratio of the particle species, and you can observe a pretty rich behavior of rise-sink transition when we change density ratio and diameter ratio. And another problem is that segregation can be triggered by different mechanisms, and the mechanisms might compete or work together. One of the major mechanisms is gravity, just as we explained earlier about the kinetic sieving. That's what we usually see on the slope or granular flow down an incline. Well, the other mechanism is shear-driven. This can be observed in problem like fault gauge, where because of the very high pressure, or sometimes the faulting is actually a lateral in a lateral direction that is proportional to gravity. So the segregation that we observe there is purely driven by shear. So how would shear and gravity-driven segregation mechanisms work together is another thing that's not very well understood. And the third problem is that from one of our research that of a binary mixture segregation in a periodic cell simulations, where we focus on how the small particle percolate downwards and large particle going upward, we can see very different behavior. Like the small particle is percolate without a lot of contact with the neighbors. And well, the large particles are undergoing enduring shear as it go up. So fundamentally, the way large and small particle migrates are different. They are asymmetric, but in most of the current continuum models, these two species are treated in a symmetric manner. So we can take a closer look at this equation and how people treat this segregation flux model. So one of the approach is the kinematics approach, where we observe or measure the segregation velocity directly from EM simulations or experiments, and then correlate this velocity with different parameters such as concentration, local concentration, shear rate, pressure, etc. And this approach is, of course, very effective because it's working directly on the segregation level, and there are models proposed to connect a lot of complex conditions to simulate size and density segregation. But for now, this approach cannot explain or tackle the challenges I just mentioned in the previous slide. And another approach that start from a little bit mechanical point of view is the stress approach by Nico Gray and co-workers, where this segregation flux model is derived based on momentum balance. And for each species of the particles, if we look at the momentum balance, we will have to specify what is the driving force terms and what is the resisting or the drag force on the right-hand side of the equation. So the driving term is based on the idea that the large or small particle take a different fraction of pressure gradient than the volume fraction that they occupy. So this is the assumption, and there are some evidence supporting this assumption, but it's still very difficult to precisely describe those different terms with the solid physical understanding. So another approach that has been emerging in recent years is the force approach, and I think this approach is started from this seminal paper in 2016, where instead of looking at a lot of particles, we focus on the single intruder particles in the granular flow first, and then really to understand what are the forces acting on this intruder particle. And then based on the momentum equation of motion for the intruder particle, which is more like a discrete version of this continuum equation, where you can still find gravity, some driving force and some resistive force. And then this can be used to describe the segregation process, at least for the intruder case. And then, so this is a scenario that for this intruder study, that if we look at the particle, and it has a acceleration on one hand, and then you have those different forces. So one thing is segregation is in most cases, as far as I observe and in a lot of studies, segregation is a very slow process. So it's nearly always, it's nearly always the equilibrium. So the left-hand side of the equation goes to 0. And then the question becomes the force balance between the weight and some driving term and drag term. And then from here, some people may assume there is a buoyancy force moving particle upward. And then the first two terms looks much like the buoyant weight in fluid case. But there are also some additional forces that I didn't list here, like the lift force, which can also contribute to the upward motion. And of course, you have a drag force to resist the motion of the intruder. But this is a very complex view. To simplify the problem, there are actually, sorry, my screen is frozen. So the problem is actually very simple, because for the intruder, there are only two forces. One force is the weight coming from gravity, but the other force is the bed force coming from all the neighbor particles in the bed. So this net bed force may be partitioned into driving term or resistive terms. But if there is a way that we can directly measure this force as a whole, and then we can have a much better idea how this force functions. And this comes to this virtual force meter, especially currently implemented in DM simulations, where the trick is that we will have to attach a spring to the intruder during shear, and then as we apply a certain combinations of flow conditions, we will observe the intruder move tends to move to a certain direction, and then the spring will hold the intruder in position, so that how much effort the spring takes to keep the particle in position will tell us the force actually driving the intruder to migrate. And the statistics coming from a spring will tell us the segregation force or the driving force. And then another thing that we've been using to really have a better understanding of the segregation force is that we are studying this in a controlled velocity flow, where we use a stabilizing force on each particles so that we can give a small kick to the particle to maintain the desired velocity profile. The motivation of this is to separate the gravity and shear-induced mechanism to trigger segregation force. And then to do that, we can use this approach to impose a homogeneous shear where the shear rate is a constant. And then we can also impose inhomogeneous shear where we can vary the curvature of the velocity profile. All of this can be done independently of gravity so that we can separate two mechanisms. And then this is how it looks like in our 3D DM implementations. And we vary the pressure, overburden pressure, shear rate, and other parameters so that we have a wide range of inertia number at the location where this intruder is. And then even though we are using a imposed velocity profile, but the rheology of the flow follows precisely the simple shear, which is a curve here. And then the main results that we found is that the segregation force can be partitioned into two terms. One term is related to gravity, the other term related to kinematics of the flow. And then there are also the drag force that can be studied individually. Well, all of those are actually by default, they have the same origin. So here I want to show you the results of the driving force induced by gravity, and then how this implies the size and density segregation, and then the driving force induced by flow kinematics, and then how these help us to understand segregation in different flow configurations. And then I want to go ahead to talk about some concentration dependence of the segregation force so that we can go from the intruder to a continuum, more continuum-like description. Well, because of the time reasons, I will not talk about drag this time. So that's pretty much the results I'm going to show. The first part is the driving force induced by gravity. So what we do here is we use this homogeneous shear so that there's no gradients induced by shear. And then we turn on gravity. The intruder is only, there are only a segregation force and the gravity acting on the intruder. And then we change the size of intruder from smaller than 1 to about 6. And then we can see the segregation force that we measure is increasing in this manner. And if you compare to the increase of the weight of the intruder because we are changing the size, they are quite close. It's more like a cubic increase, but there are some small differences. So if we take the ratio of the segregation force over the weight, we can see actually there are considerable difference at different size ratio. Like here, it corresponds to the size ratio around 2. That's where the segregation force pointing upward is higher than the weight. So the particle will rise. And then this is where the weight is too heavy, that is greater than the segregation force pointing upward. So the intruder tends to sink. And we also change the density ratio of the intruder. But here we found that if we change the density of the intruder itself, it doesn't change the result very much. Well, if we, but at the same time, the weight of the intruder has been changed a lot because we're changing density. So if we again take the ratio, we can see light intruders rise all the way, while heavy intruders will always sink. So it's really a balance between the segregation force and the weight of the intruder. And similarly, we can also change the density of the bite particles. And then we end up with three curves here for different density ratio. And then what we do is we do a scaling analysis. We think this segregation force is really scales like a buoyancy force. So because it's proportional to the pressure gradient, that's the only gradient in the problem. And then we can derive, come to this relation for the segregation force under gravity. That is, it's a buoyancy force, but you have a prefactor Fg that is a function of R. So if Fg equals 1, this goes to the Archimedes limit for continuum fluids. But here, because of the discrete context between particles, we have some this peak behavior for the F function. But the second case, so here I want to talk about the implications of this model for size and density segregation. So as I said, this is purely a balance between two forces, and we have scaling for the segregation force is pretty much buoyancy. And then we can set the two forces equal, and then we cancel some terms. We come up with this neutral curve where the particle will not go up or down. That is the density ratio and versus size ratio. We can plot this in a phase diagram, which tells us where this neutral curve occurs, and below the curve, the particle will rise, and above the curve, the particle will sink. We test this with the experimental results that has been done like 17 years ago. And this is done in different geometries like rotating drum, pile formation, and the chute. And we found that where Z detected the particle to be neutral is pretty much following the prediction that we have based on the simple force model. And this is where the large particles rise, and this is where they sink. So we think this simple force balance between the buoyancy-like segregation force and the weight of the intruder can explain the combined size and density segregation. So next, I'm moving to the driving force, that segregation force induced by the shear gradient. In this case, we turn off gravity completely, and then we change the shear profile from linear to nonlinear, and we have positive and negative curvature. And then here is the result. This is the velocity profile when it is linear, and this is curvature smaller than 1, and smaller than 0, and greater than 0. And we can see if it's a linear velocity profile, the intruder displacement is pretty much at 0. So there's no net movement for the displacement for the intruder. And if it's a negative curvature, the intruder tends to go down. Well, if it's positive curvature, it tends to go up. So this is completely driven by the shear gradients, and we can write that the segregation force when gravity is 0 is proportional to the shear rate gradient. And then again, based on dimensional analysis, here we only have pressure, shear rate gradient, and the diameter of particles. And we can write down this scaling for the force and the shear rate gradient. We come up with this force model that the segregation force induced by shear gradient is something like this. And then we have a prefactor Fs that's also a function of the size ratio. And this curve looks qualitatively like the one for the gravity term, but you will see this goes from negative cross 0 to positive. That's a major difference. And also this is not very sensitive to inertia number as the other case. And now if we put the two terms together, we have a gravity-induced term and a shear rate-induced term. And then both terms have the prefactor F that is a function of R. They look pretty similar. And if we look at think about the physics, why it looks like this, when the size ratio is smaller than 1, the particle percolates through voids. So the force we measure in this case is smaller than the buoyancy force for a fluid. But when size ratio is 2, we have some really discrete context that makes the force goes to a peak. And then as we further increase the intruder size, this goes to the continuum limit, where it should follow the Archimedes principle. And also, if we look at the curve, it's actually not symmetric around R equals 1. That means small and large particles, they behave differently in terms of the force acting on it. Now, we can also try to test if this model works for other geometries. So far, we measure this force separately in our controlled velocity geometry. And here, we test this prediction for wall-driven flow, vertical silo flow, and inclined chute flows. And this prediction does not involve any refitting. We use the same parameters we obtained from independent tests. And the prediction for R equals 2 shown here is perfect. So this means that if you look at any of the geometry here, there are two mechanisms working together. Like for this wall-driven flow, we have gravity, give us a positive force, and we have a positive curvature give us another force acting upward. So these cases always have a positive segregation force. Well, if we look at this inclined chute flow, because this second term, the shear rate gradient, is really small compared to the first term. So it's almost a pure gravity driven case. And we can see this inclined chute always have these positive forces here. And for the vertical chute, this is driven purely by the negative curvature. And you can see the forces are always negative. Okay, so now let's move on to the third part where we want to extend this approach to bias mixture, because we don't want to focus on intruders. And in order to do that, we will have to increase the number of intruders, and then we apply the same idea of using a spring to measure the force. And then in this case, we actually apply the spring to the center of mass of a group of large particles, and then we can reach a force balance where the segregation force is balanced by the spring force and the weight of each individual intruder. And then as we change the concentration of the intruders, we can come up with a function between the segregation force and the concentration. And we can also do this for different density. And in that case, the density has to be calculated based on the volume fraction of particle species. And then we first verify if this spring approach works. And what we do is we compare this single intruder measurement with a mixer measurement where the intruder concentration is close to 0.1. And then that's where the large particles actually do not see each other very much. And we can see these results agree very well with our single intruder measurement. And then we can, for example, with size ratio equals 2, we can continuously increase the concentration of large particles, go from the single intruder limit to a binary mixture to another monodisperse limit. And then we can plot the results against concentration. And here we already have 2 limiting cases. One is a single intruder case that we just measured. The other one is a monodisperse limit where the force just simply balanced by the weight. And in between, we found that there is actually a rather continuous transition from one limit to the other. And we observe a plateau here, indicating that when the concentration is small, they do not, large particles do not interact with each other, and is consistent with the intruder limit. And of course, there's a critical concentration where they start to cooperate, and then the force will decrease in a nonlinear fashion. And we can fit this to a certain function and describe this. And also, this is another source of built-in asymmetry about concentration in terms of the segregation force. And now, since we know the dependence on concentration, we can actually derive the stress in a homogenization kind of manner in the control volume from particle forces. So this function actually serves as a bridge between the microscopic particle level forces and the continuum level stress gradient. And then this result is actually about to appear in GFM very soon. And then to summarize, we provide a unified description of the segregation force due to different mechanisms, and we actually can partly answer all the 3 questions that I posed in the beginning. And then we are currently working on the resistive strike force, but we also work on the concentration dependence so that we can go from the particle level to the continuum level. Thank you so much.
Thank you very much, Lou, for this excellent talk. It was very nice. So do we have questions? Chris, go ahead.
Hello. Thanks for a great talk. Yeah, I really like this work you've been doing on this stuff. So a couple of questions, actually, both of which are in that slide. One of which is, so the first one of which is the dimensional analysis that you are doing. You are including a gradient of the pressure in that dimensional analysis. Is that right? And a gradient of the shear rate?
Yeah, so for the shear rate gradient case, that's a case where we don't have gravity, so there's no other gradient.
There's no other gradient.
yeah, the only gradient is what we impose, the shear rate gradient.
So maybe it's me as a mathematician saying this, but I would claim that you cannot do dimensional analysis on non-uniform quantities like that, because the dimensional analysis is built around the global parameters of the system. And
I see.
Essentially, there's an assumption of local dependence on shear rate or on gradients.
Mm-hmm.
So I would say that you could, in principle, if you were going to include the first gradient, dp dz, you could include the second gradient, the third gradient, and so on. And those should all come into the dimensional analysis. And then quickly you have infinitely many parameters. So that's something slightly technical, but it comes up quite a lot, I think, in attempts to do dimensional analysis on granular segregation. And
I see.
you then go on to show that there's good evidence empirically that is a good idea.
Right, you're right. Yeah.
The first derivative seems like the most plausible thing, but I think strictly one cannot use the Bucky and Pi theorem and all those things from dimensional analysis for that. So, but I'm happy to discuss that later if that's of interest to you.
For sure. But sorry, how about this? So we probably is partially dimensional analysis. So we first get this empirically that the force is propensity gradient, and then we normalize shear rate by gamma dot.
That's fine.
That's actually what I'm doing. So it's still on the system parameter. Yeah. But we get this.
Yeah,
we get this relationship empirically first.
Yeah, you can make an assumption, but not everything comes from dimensional analysis.
I see.
I just wanted to note, it's on slide 19, which was very interesting to me. Am I right in thinking that you're on the right-hand plot? It appears that your model is predicting that there is a peak in segregation rate at a concentration which is about 0.2 or something. It's slightly higher there than at. Do you think is that a physical prediction that you think is true, that actually adding more large particles will increase the segregation rate, or is that just something to do with the function you're using to fit?
I think, well, we think there is actually no peak, because from physical intuitions, as you add particles, they do not see each other. So there has to be a plateau. And that's actually the major constraints that we have to derive the model. If you look at the paper later on, you will see how we constrain the model very strictly based on that understanding. But then in terms of the peak, I agree that here for this particular plot, you see something like a peak. But if you look at the paper, we have many different cases. It's more like a fluctuation, because when you get to this small concentration. Yeah.
I actually mean in the red line that you've got there, it looks like there's a very subtle little maximum just at about concentration is 0.15, and it goes down just to, is that true? But
no, this is it's an illustration. It's not a mathematical
fine
curve. So if you look at the paper, the function we use is it's more like a sigmoidal. It's a hyperbolic tangent function. Because another thing I didn't mention is for large particle here is a plateau, and for small particle it has to be a plateau as well. So if you plot this in the other way around, for small particle concentration, the plateau will appear for the other small particle intruders. So the two ends both has to be plateau, and there is a linear transformation as well. So that makes us choose the final function we use. We thought is very well constrained by those physical understanding.
Okay, thank you very much.
Thank you very much, Chris.
Thanks for the questions and comments.
Miguel, go ahead, please.
Thank you, Yuri. Oh, my video. Now it can be on. Congrats, Jing, for your work. I had a question about the final model you present at your very last slide. What will happen if you don't have shear strain rate? So if you have a plug flow.
Can I just interrupt, Miguel? Lou, I think we lost your screen. Are you there?
Oh,
Yeah, and his video also froze.
Yeah, we lost you somehow. Your video.
if there's no shear, there's no segregation.
Ah,
You're there. We cannot see you.
Go
Go ahead.
Can you hear me?
Yes, we can hear you.
Yeah.
We cannot see your screen.
Yeah, it's a little bit kind of. I see.
That's
so it's
fine.
unstable
Go ahead.
here, but I mean, it's a good question. I think for the plug flow, the problem that we are thinking is, it has to be in our case, it has to be granular flow driven segregation. And if it's a plug flow, you don't have flow in the shear flow in the first place, then it might become a different problem. So another thing is, because of shear, we create these granular fluids. So all the buoyancy-like force or the other forces, there's a lot of similarity with fluid forces. So we need a granular fluid first, and in our case, is created by shear. So I don't think plug flow work exactly the same. But we have been measure the force very close to the plug zones. Like we have a plug zone, we have a shear zone, and that's during the transition, we actually go to a very small inertia number, like the non-local regime. And I think that's another kind of big question, whether this model works for non-local rheology regimes. But that's a different question.
right. Just to comment on that, is because if I feed your equation on the force of segregation, and I assume that the shear strain is 0, I still have a term that would lead me to have a segregation force. But that is difficult for me to imagine.
Yeah. That's actually possible. If you think of a vibration system where you don't have shear, you don't have net shear at all, it's vibration, and you measure the force, you will get this buoyancy force. So the first term that is buoyancy, as I said, the condition is you need a granular fluid. So the granular fluid either induced by shear or induced by vibration, it doesn't matter as long as you have some kind of granular fluid behavior. I believe this buoyancy term will pretty much work, although the fine details of the F function might be different.
Thank you.
Very good. Lou, thank you very much.
Thank
very
you.
Nice talk. Thank you. I'll stop recording.